Grad school life. Okay. All right. Week 3. So today, well, okay, wait, what did we do? Okay, last week we did randomization methods. So things like the randomization test and bootstrap and cross-validation. Yeah, exactly. Okay. And and so this week we are going to look at decision trees. Okay, decision trees is kind of the overarching topic, and there's regression trees and classification trees. Those are both decision trees. And then we've got methods to improve tree performance, which includes bagging, random forest, and boosting. And boosting is actually a generic idea that can be applied to a bunch of different kinds of statistical models, but I would say it is easily applied to trees, and it's frequently used on trees as well. So we're going to look at boosting in trees. I don't know if have you guys heard of boosting? There's a popular package out there for machine learning called XGBoost, which is okay. Well. So if you've heard of XGBoost, it's a boosting method. If you haven't heard of XGBoost, no worries. It's just a hot method that's applied to stuff. Okay, this stuff is covered in Introduction to Statistical Learning, Chapter 8, and Handbook to Statistical Analysis Using R, Chapter 9. You can always also look up decision trees. It also goes under other names like CART, which is classification and regression trees, but somehow, so classification and regression trees is probably the best name, but whoever came up with that trademarked it, and so now we can't use that without giving, I don't know, something to that guy. So we call things like tree-based methods and recursive partitioning, but you might also see CART, and you can look up capital CART to look this stuff up as well, classification and regression trees. Okay, so the big idea is that a decision tree is going to partition the data into smaller chunks. Here, let's just go ahead and do this. And basically, at each split, the tree is going to use one explanatory variable. So you can have a whole bunch of variables in your data set, but each split happens at for one variable, and it creates a binary split. You either get a yes or a no. You either go the left or the right branch. Okay. If the explanatory variable is numeric, it's going to be of the form you got some number k, all right, and you just say, all right, is x less than k, yes or no? Okay, and either it's yes and you go down this side of the branch, or no and you go to the other side of the branch, okay? Or if it's categorical, it's going to be is x either this or this, okay? And either it is, so is your value in categories A or B, or it's not, okay? And you go down this side of the branch or not. And then you keep doing this binary splitting until you reach some kind of stopping criterion, okay? And after all the and so here's the thing, after all the partitions have been made, okay, and you with a decision tree you can kind of say all right, you kind of follow the thing, and then you go down and it just makes one prediction for all the observations that fall into that quote partition, okay, that partition. So you just kind of follow the tree, you go down the path, you end up in a partition, and everybody in that partition gets the same prediction, okay? Either we predict a categorical value for that, or we predict a numeric value, okay? And so if there's 30 people there, all 30 people get the same prediction, okay? So there's it's not like linear regression. In linear regression, you plug in a value, even with simple linear regression, there's infinitely many predictions that you can make, right? So if your prediction line is 2x plus 1, you plug in 0.5 and you get, 2 times 0.5 plus 1, which is 2, and you plug in 0.51 and you get a value like 1.02 or something like that, okay? But here, probably x equal to, I forget what I was saying, but x equal to this, like 1 and x equal to 1.1 would probably end up in the same partition, and you would get the same prediction for all of those, okay? And then, so anyway, we've got regression trees and classification trees. Regression trees predict a numeric response, and classification trees predict a categorical response, okay? So actually, before we get into regression trees, go ahead and turn the page, and I've got an example of they created a decision tree in the New York Times back in 2008. So this is like super long ago, okay? This was back when George W. Bush was still president, and there was the primary between Obama and Clinton at the time. So this was before Obama was elected, and there was a primary who would be the Democratic candidate. And so here was a decision tree trying to figure out who might win the primary, okay? And so this was a decision tree, and this was published in the New York Times, and so this, well, let's just ask, is this a regression tree or a classification tree?
Classification.
Classification, right? Because we're trying to predict a categorical output, and the category is either Obama or Clinton, right? Who's going to win this thing? And so they looked at all of this county level data of the people, I think, who have kind of, I don't remember. I think it was so far, like at some point in like kind of the primary process, like some places had already voted and some places hadn't, and they were trying to do that, okay? And so it'd be something like, we're looking at, there's different variables, okay? So one of the variables was the proportion of this county that was black, okay? And basically, some counties are 0% black, and some counties are 99% black or something. There's possibly, okay? There's a spectrum, okay? And so the decision tree figures out that, let's look at this threshold, and the decision tree figures out the threshold, and the threshold was 20% black, okay? And it was, if the county is more than 20% black, then if that's a yes, then Obama wins these counties 383 to 70, okay? So there was 403 counties, I guess, and that, okay? And so, and if not, then we go down and we ask another question, right? And so, and again, so now another variable that was available in the data set was the high school graduation rate, okay? What percentage of the county had graduated high school? And again, some counties, the number's very low, and some counties, the number's very high. And the decision tree figures out exactly where this partition should be, okay? And it says, okay, we're gonna draw a partition at 78%, okay? It feels a little arbitrary, but it's, we'll talk about how it comes to this number, okay? And so it says, okay, at 78%, this is a county with less educated voters, and Clinton won these, 704 to 89 or something like that, okay? And so on and so forth, using the same variable, high school graduation rate, okay? So if it's less than 78%, then it goes to Clinton, and if it's greater than 87, then it goes to Obama. Now you'll notice that these are not, there's still, it's not a perfect prediction, right? 784 to 89, okay? Which means if you are a county that is less than 20% black and has a high school graduation rate lower than 78%, this decision tree is going to predict Clinton, okay? But it's going to be wrong 89 times out of however many this is, 793, okay? So there's 793 that fit this thing, and for all of them, it predicts Clinton, but many of them, 89 of them don't go that way, all right? And then so, you can kind of follow this, and it just keeps splitting further and further. Is it, in the Northeast or South? Is it the West or Midwest? Is it blah, 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 blah? And it, finally it kind of splits in this way, okay? And so that's basically how decision tree goes, okay? So it's just at the end, we call these terminal nodes, okay? So you've got basically a node that will split, and then if it ends there, you call that a terminal node. And basically, once you reach a terminal node, it makes the same prediction for everybody there. And there's going to be some misclassifications, but that's how it goes, okay? Is that all right for how this works? Okay. I don't even, we have a wide range of students in diversity. So some of you might have only been 12 or 13 in 2008. I don't know, okay? Okay, so anyway, we're going to first start off just talking about regression trees, okay? Type of decision tree used to predict or model a numeric response. And as far as where do we choose the partition, okay, the tree is actually going to consider every single possible partition, okay? So if you've got 100 data points in your test set, it has 99 partitions to consider, okay? And it's going to consider every single one of them. And decision tree algorithms are greedy, and what that means is that it's going to say, all right, let's look at the RSS that we have without the partition. We're going to look at every single possible partition in the data set, and we're going to look at the resulting RSS after we make the partition. Okay, and I'll explain all of this, right? But so we start off with, this is where we are now. We're going to look at every single possibility, and whichever possibility gives me the most improvement, I'm going to pick that one, okay? It can't think 2 steps in advance, okay? It can only think to the next immediate step, right? So, there might be some case where you want to do something a little bit less optimal now so that you can do something even better in the future, right? The decision tree doesn't have this kind of look ahead thing. It just says, what's the best right now, okay? What's the best right now, and it goes for it. Yeah.
So does that mean that the order of variables you look at in a decision tree matters in terms of the results?
No, it's going to look at all the variables and all possible partitions.
Okay.
And then considering all variables and all possible partitions, is going to choose the one that gives the best immediate gain. Okay. So you might for example, when it was doing this, it was looking at basically every single possible partition, and let's there were a lot more variables, but let's say our data set only had these 2 variables, what percent is black and what percent graduated high school, okay? And so basically before it made this decision, it said, I'm going to look at drawing a cutoff at percent black 1%, and percent black 2%, percent black 3%, 4%, 5%, all the way up to 99%, okay? And it looks at all of those. And then it goes to, and I'm also looking at high school, and then I'm going to split at 1%, 2%, 3%, all the way up to 99%, right? It's technically not that, it's looking at the data points and things like that. And then it says, okay, considered every single possible partition I could make for percent black. I considered every single possible partition for high school graduation rate, okay? And there might have been a couple hundred possible partitions, and it says the one that gave me the best score was if I split at 20% black, okay? And so that's where it goes, all right? And so it creates that split, and then it goes on and it says, okay, now I'm going to look again at percent black, every single percentage, and percent high school, every single percentage, and it considers every single one of those, and then it says, okay, the one that gave me the best split now was high school at 78%. Okay, and it does that every single step. Now this would be very painful to do manually, but with the computer it's not so bad. Okay, but to illustrate, we are going to do it manually on a very small data set. Okay, and so this small data set only has 1 predictor variable and 1 outcome variable, or 1 response. But if we had multiple predictor variables, we would just consider every possible partition on the X, and on the first predictor, and every possible partition on the second predictor variable, and we consider all of them, okay? So here, we're just going to try making one, this is all the work, like I've got like, I don't know, the next 5 pages are all just to figure out the very first partition on this very small data set, okay? And so we could see this is a lot of work, but the computer has no problem doing it. Okay, so here's our original data. X goes 1, 2, 3, 4, 5, and Y goes 1, 1, 3, 7, 8, okay? And so right now, before we do any kind of splitting, all of the values are in technically one partition. They're all in the same thing. There's no splits. And so, like, if this was the terminal node right now on, basically, I guess it's not even a stump. It's just, if this was the terminal node, okay, basically, we would look at the average of y, the mean y, and we go 1 plus 1 plus 3 plus 7 plus 8 divided by 5 is 4. Okay, this adds up to 20, and we divide by 5, and the mean is 4. And we would calculate the RSS. So we say, okay, here's the actual y. We are going to predict 4 for every single observation. Okay, that's the kind of the thing is that every observation in one partition gets the same y hat prediction, okay? And then we calculate the sum of squared error, okay? Or the squared residual. So the residual sum of squares, the RSS, your residual sum of squares is going to be 44. So we say, the actual value is 1, the predicted value is 4, that gives me a residual of 3, I guess technically negative 3, and I square it and I get 9, okay? And I do that, negative 3 squared is 9, negative 1 squared is 1, 3 squared is 9, 4 squared is 16. I add all of these up, and the RSS is 44. And here's kind of a picture. I got 1, 2, 3, 4, 5, and y goes 1, 1, 3, 7, 8. And right now we are just going to say everybody we predict 4. Okay. Is that good? All right, so this is our baseline, okay? And we're going to say, all right, what split, I'm going to consider all possible splits. So I have 4 possible splits. I can split between basically at 1.5. I can split at 2.5, 3.5, and 4.5. Okay, so I'm going to consider all 4 possible splits, and we're going to look at how the RSS is improved when I consider each of these splits. Okay, so the first I'm going to consider making a split between x is 1 and x is 2. Okay, so I'm going to consider a split at basically x 1.5. All right, and so if I do this, okay, if I make the split, okay, so now I have partition A and partition B, okay, for values less than 1.5, I've got 1 observation, okay, and so only y is 1 is there, and therefore my y hat for this observation, for this partition is 1, okay, and I have no residual, no RS right here, no residual squared there, okay, I've got 0, okay. For the other 4 observations, end up in this partition, and so I take the average of these 4. So these 4, I do 1 plus 3 plus 7 plus 8, which adds up to 19. I divide that by 4, and I get 4.75. And so for this partition, my y hat is 4.75 for everybody. And we calculate the residual for each of these. So I do 1 minus 4.75. So I'm leaving off the negatives. I don't know why I left off the negatives for all of these things. But we got negative 3.75, negative 1.75, 2.25, and 3.25. I square each of these. I get 14 point something, 3 point something, 5 point something, and 10 point something. And if I sum all of these up, so I have a 0, but I've got a bunch of numbers here, my RSS here is 32.75. Okay, so I went from 44 with no partition, and if I split between 1 and 2, if I make a split at 1.5, I get an RSS of 32.75. Does that make sense? Okay, all right. I do the next split, okay? All right, so here, partition A is going to be all the values less than 2.5, all right? And partition B is going to be all the values greater than 2.5, okay? And so when I look at my data, all right, for the values less than 2.5, both of the values there are 1, okay? Y is, for the first observation, Y is 1, the second observation, Y is 1, and so therefore my Y hat is going to be 1. It's the average of those. I get 1. And I have no residual, and my residual squared is also 0 for both of those observations. Okay. For the other 3 observations, okay, 3, 4, and 5, for x is 3, x is 4, and x is 5, my y's are 3, 7, and 8. Okay. So I take the average of those. 3 plus 7 plus 8 is 18. I divide by 3, and so my prediction for all 3 observations here is going to be 6. So I take 6 and I calculate the residuals. 3 minus 6 is negative 3, 7 minus 6 is 1, 8 minus 6 is 2. I square them, I get 9, 1, and 4. Okay, and I add up all of the residuals and I get a total RSS of 14. All of the squared residuals, I should say. Okay, and so this one has better performance than this one. This one had an RSS of 32.75 and this one has an RSS of 14. Okay. So it's even better, all right? Okay, and then I consider this split, all right? So we're going to split between x is 3 and x is 4, so basically at 3.5. Okay, so values less than 3.5, y takes on the values 1, 1, and 3. So therefore, my y hat is going to be 5 divided by 3, 5/3. Okay, and then for values greater than 3.5, y takes on the values 7 and 8. Okay, and so my prediction for all of these, for both of these observations here, will be 7.5. Okay, so I do, so 5/3 is 2 2/3. No, what did I do? Okay, wait, what? I'm sorry, is 1.67, okay, 1 2/3, okay? So if I do 1 minus 5/3, I get negative 2/3, and I just take the difference, negative 2/3, and 3 minus 5/3 is 4/3, okay? And then over here, the residuals are 7 minus 7.5 and 8 minus 7.5, and I get negative 0.5 and 0.5. And when I square these, I get 0.444, 0.444, 1.7778, and 0.25 and 0.25, okay? And when I total up the squares of these residuals, the RSS, residual sum of squares, I get 3.1667, okay, which is our best performance here. So we can see kind of the residuals from here. And again, our prediction, these blue lines represent the prediction for all the observations in this partition is, so this is the blue prediction, and we can see the residuals that we have, the difference between our prediction and the actual value. Okay, and then finally, I will consider the last possible partition, which is going to be between 4 and 5. And we would get the y values in partition A will be 1, 1, 3, and 7, which will give a mean of 3. And then the y values for partition B is just 8, okay? And so here I calculate the residuals, okay? So I get -2, -2, 0, and 4, and 0. And then I square those residuals, and I get 4, 4, 0, and 16, and 0, okay? And so if I sum up these things, the total RSS of this split is going to be 24, right? And so we can see, you know, this is probably not the optimal choice, okay? Because even though it predicts this value perfectly, you know, there's a huge residual here and pretty big residuals over here, okay? And so, so anyway, that's what we have. Okay, so we've looked at all 4 possible partitions of our data. And the one that had the best resulting RSS was the partition between 3 and 4, okay? And so here, this one has the smallest resulting RSS of 3.1667, and so that is going to be the partition that we choose, okay? So we would choose a split between x is 3 and x is 4, and that's going to reduce the RSS. So before, we had an RSS of 44 with no partition. After the partition, our RSS is 3.1667, and that's how we would choose just on this case, okay? And so, you know, if you had a large data set, so basically, if you have n observations, or I should say, if you have n unique x values, all right, then you've got n minus 1 possible partitions, okay? So generally, you will sort them from least to greatest on x, and figure out possible partitions. If you've got a categorical variable, okay, then you have n choose 2. So if you have, if you have k categories, okay, then you have k choose 2 possible partitions. So if you've got A, B, C, D, you've got A versus B, C, D, you've got A, B versus C, D, okay, let me start over. No, how many? Maybe it's not k choose 2. It's k permute 2? I don't know. Okay, so if you got 4, you've got a whole bunch to consider, right? You've got A versus BCD, B versus ACD, C versus ABD, and D versus ABC. And then you got AB versus the rest, AC versus the rest, AD versus the rest, BC versus the rest, and BD versus the rest, and CD versus the rest, okay? And then once you get to the other, then everything becomes redundant, because once you start looking at 3 versus 1, it's all the same as the 1 versus the 3, right? So ABC versus D is the same as D versus ABC, which you've already considered. So I forget.
But you also can't just choose all of them and put everyone in the same group.
Yeah, because that's no partition,
yeah.
right? Yeah, so you have to consider all of them, and maybe you know, anytime you pick a partition, it will reduce the RSS, okay? But yeah, we'll talk about how to decide whether to even consider using a single partition or not, okay? So with categorical ones, you got to consider all possible splittings of the categories, and then with numeric, you have to look at all of your unique values that you have in the x variable, and you consider all of them, okay? And if you have multiple variables, okay, so here we had 4 possible partitions to split because we had 5 unique x values, right? So it's not the number of unique y values, it's the number of unique x values, and I had 5 of them, so I had 4 possible partitions to split. And if I had a second x variable, I would consider all possible partitions on that second x variable as well, okay? So if I had like a second x variable, and there was 5 unique values, then I would have another 4 partitions to split, consider. And I would have a total of 8 partitions, and I would just pick the one out of the 8 that would be the best. Is that okay? You look... You didn't get that part. Okay, so
I understand the 5, and then you have 4.
Right.
Second set.
Yes. Okay. So let me just take out my pen here, and so basically, we're considering every possible partition, every possible split. Okay. So okay, so here I think in this one I had x's 1, 2, 3, 4, and 5, and so I'm going to call this x1, and then let's pretend we have another x2 variable, and this has values I don't know, 11, 12, 13. 15 and 7 or something like that, okay? And then y, you know, the values don't even matter, right? Okay, so first we consider x1, and then the possible partitions are x1 less than 1.5 versus x greater than or equal to 1.5, okay? And then the other splits are x1 less than 2.5, less than 3.5, and less than 4.5, right? So these are all the possible splits on x1, right? And then we can look at x2, right? And basically, you know, I have to kind of sort these from least to greatest, all right? And then so we'll also consider x2 basically less than, it doesn't even matter what numbers I pick, but I can just do like 7.1, x2 less than 11.1, x2 less than 13.1, and wait, 11, oh, I'm sorry, I missed the 12, okay? 11, 12, and 13. Okay, or whatever, right? The decimal point is arbitrary, right? Okay, so so I consider all of these possible splits. Okay, so now there's 8 of them, and I look at all 8 of them. So we look at this, and we get an RSS, resulting RSS for all of these, and you know, maybe I think, I don't remember what the numbers were that we had when we went through this. We had 32.75, and we had 14, and 3.1667, and 24. And you would look at these, and maybe it's like, you know, I'm making these up, 17 and 20 and 8 and I don't know, 2.1 and 16 or something, okay? And so considering all of these, you'd say, oh, the best one is this one, whoops, is this one right here, okay? So considering all possible, 8 possible partitions, this is the best, and so that's the one we choose. Does that kind of make sense, what's happening?
So when you choose it, do you have, like, it seems like you have all x1, x2, put them together and line them up?
Well, you're not putting them together. You're considering all possible splits on x1, and then you also consider all possible splits on x2.
But there is no like a two-step way. So
it's not 2 steps. Yeah, it's you're looking at all possible partitions on all possible variables. So there's 4 possible splits for x1 and 4 possible splits for x2, and you consider all 8 possible splits, and then you choose the best one from all 8. Correct. Yeah. We're not saying I want the best partition on x1 first, right, and then the best partition on x2. No, we look at all possible partitions on x1, all possible partitions on x2, and out of all 8 possible partitions, we pick the best split.
So then is the next step just looking at x1 essentially twice for these new partitions? Yes,
okay. So all right, so let's say this is the split that happens, okay? And so so now we have x2 less than 12.1, and over here we have x2 greater than 12.1, and so my data set here, I have to, let me see. Okay, so I'm gonna just circle these, okay? So less than 12.1 gives me this, and this, and this, and then the other side will be this and this, okay? And so now I have x1, x2, and then y, and we go 1, 2, 5, 11, 12, and 7, okay? And then over here, so this is my data set, and then over here my data set is x1, x2, and y, 3, 4, 13, and 15, okay? And then I would consider, now I have 2 possible splits on x1. Okay, so I would have x1 less than 1.5, x1 less than 2.5. So the possible splits I have here, x1 less than 1.5, x1 less than 2.5, x2 less than 7.1, and x2 less than 11.1, right? So there's 4 possible splits here. I look at all 4 of them, and I choose the best performing one. Okay, over here there's only 1 possible split. x1 less than 3.5, okay? Which is exactly identical to x2 less than, basically 13.1 or whatever, okay? These two happen to be equivalent. These ones, there might be, I think these two happen to be equivalent as well. x1 less than 2.5 is equal to x2 less than 7.1. I think those two splits are also equivalent, okay? Because basically you're drawing there and there. Okay, so actually these and these two are equivalent as well. Okay, so there's only a few ways to actually split the data and stuff, but you're going to consider all of them. That's the point. And yeah.
So is one big difference between this, your example here, and the Obama-Clinton example is that you can partition on the same variable multiple times throughout your decision tree?
There's no difference between this and the Obama-Clinton one.
Okay.
Yeah. So the first split, according to this example that I've just made up, my first split was on x2.
Yes.
Okay. And here, my next split down here could also be on x2.
Okay.
Okay. Or it could be on x1. Okay. We just look and we say, all right, the resulting RSS if I make this split is going to be this, 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 or this, right? And it could be like 12 and I don't know, 10 and 10 and 12 or something, and we go, okay, well, this is the split I choose, okay, and we say, okay, well, I'm going to choose this one because it's the best performing one. Yeah.
Could you have a case where you have two variables that have the same RSS?
Two possible splits that have the same RSS.
Yeah.
Let me think.
X1 and X2 that use the same length.
Yeah, that's possible. Okay, you can have you might, as you're lining these up, and you're considering different possible splits. Okay, so I shouldn't say variables, but you can have one possible split results in RSS of 2, and then this other possible split also ends up with an RSS of 2. Okay. That could happen. How do you decide then? There's no guidance there. Okay, it's a little bit arbitrary. I would say that's maybe not as common for a regression problem. Maybe a little bit more common for a classification thing, and I'm not sure how. Our part makes its decision there. Okay. Okay. Does this kind of make sense for like multiple variables and stuff? All right. So let me. Okay. All right. If we want to do this in R. There's a few packages we can use, okay? There's tree and there's rpart, okay? Now, the textbook, Introduction to Statistical Learning, uses package tree. And textbook to Handbook of Statistical Analyses uses rpart. I think rpart does a better job than tree, okay? That's my personal opinion. I don't know, I feel like the internet generally agrees with that as well. You can use either, but I think rpart has a few nice features that make for kind of setting up your trees a little bit nicer. Okay. So anyway, I'm going to just show how to use rpart in this thing. So rpart stands for recursive partitioning. Again, it's all the same idea. Recursive partitioning. They call it that because you do a split, which is called partitioning, and you keep applying that partition strategy recursively on each resulting partition, right? It's just a decision tree, okay? It's a decision tree, classification regression tree, but again, CART was trademarked, so we can't use that, so we're coming up with all sorts of other stuff. So rpart I guess rhymes with cart, and I don't know, maybe that's why we do it. Okay. So anyway, in our part, you specify a formula, okay, such as y tilde x. If you've got multiple variables, you can do y tilde x1 plus x2 plus x3 or whatever. You know, you've got, you're familiar with the LM formula notation from your 402 class, right? So it kind of works like that. It's just the idea, and if you're not in 402, don't worry. It's just you've got the output variable y tilde the input or predictor variables x, okay? And if you've got multiple ones of these things, you just kind of list them off and you put pluses in between them, okay? Or if you want to just do all of them, you just do a dot and it's going to do all of them, okay? So you do y tilde x, and this is, you know, predict y based on x, or y as explained by x, okay? You have to specify the data, where the data is coming from, and then there is this attribute called control, which tells you how you should split the tree, okay? Now, by default, the minimum number of observations to consider a split is going to be around 20, is what the thing says. But in order to do it on our tiny data frame where we only have 5 observations, we're going to change this and say consider a split even though there's only 5 observations, okay? That's all we're going to do. All right, so anyway, I get my data into R by doing this command here. I say create my data frame, data.frame, x is this and y is this, and this is the exact data that I have, right? And then it also adds row numbers, which is incidentally the values I used in my x, but that's just an like coincidence there, okay? And then, and here I say make a tree, store in tr, short for tree, whatever you want to call your variable or result is, whatever. And I have our part, y tilde x as explained by x. Data is this data frame that we have. And control here, I have to specify consider a split even though there's only 5 observations, okay? Normally R would just say you only have 5 observations, just throw them in one partition. I don't want to split it any more than that, okay? But we say consider a split even though you only have 5. And we see here's the results, okay? And this is, you know, it's a little bit hard to read here, okay? But it says, here's the node number is 1. The split happens here, okay? The number of observations is n. The deviance is this number, and then you've got y val, okay? And if it's a star, it's a terminal node, okay? So here, we start, there's no split, okay? The first node is the root, there's no split there. We have 5 observations. The deviance, which is kind of our RSS, is 44, and we saw that earlier when we calculated when everything was in the same thing. And then if we didn't split it, our prediction for all observations would be 4, right? And that's exactly what we had back on this page right here, right? So we said our prediction for everybody would be 4, and the RSS with no partitions would be 44, okay? All right, and then over here, the next line says at node 2, the split happens for x values less than 3.5, okay? And if you do that, there will be 3 observations resulting in that partition, and the deviance there is going to be 2.667, and the predicted value for all observations in that node is 1.667, okay? And it indicates this is a terminal node, okay? Same kind of information. 2 in that one. The total deviation there, RSS, is going to be 0.5, and the y value prediction is 7.5. So this again is kind of the results that we got here, where if I add these up, I would get that 2.667 value. We can see that our prediction there is 1.66, and then the prediction over on the other node is 7.5. We have 2 observations, and the total deviation, if I added those up, would be 0.5. Okay, so this matches exactly what we got when we did it manually by hand. All right, nice. So I think I've written all of that. Okay. Any questions on kind of this output? So this is gonna just be what our outputs when you say make a tree. Right, and again, you just kind of read this as kind of the decoder for each of the values in these columns here. Yeah.
Is there a way for R to show you the other partitions that didn't have this?
No, it doesn't print out the suboptimal partitions. It just says this was the resulting tree. It doesn't. You just have to trust this was the best one, okay? And it's reliable, okay? So you don't have to worry about all of the other suboptimal splits, okay? Once you've created a tree, okay, you can, so here I've created this tree. I said the result of R part store and TR, okay, so I've created this tree. You can also call summary on the tree, okay, and it will give you a bunch of relevant information as well, okay? And so one thing here is the complexity parameter, okay, which it calls the CP, all right? And it figures out some other stuff here. So let me let's look at this thing here, okay? So node number 1 started off with 5 observations, and it says the complexity parameter is 0.928, all right? Okay. Here it says the mean is 4, okay? So again, that would be the value it predicts, okay? The value it predicts for all 5 observations is 4, and the total RSS was 44. Oops. That's my tile. If you click your keys, it'll find your phone. Even if it's like silenced, is the thing. Okay, or you click your phone and you can find your keys. Or you can ask Alexa to find your keys for you. Okay, so anyway, so our total RSS was 44, and if you do 44 divided by 5, you get 8.8. So it's kind of saying the mean squared error is 8.8 here. Okay, let's talk about where this improvement comes from, this 0.928, which incidentally is also this complexity parameter here, okay, which is they're very much related, okay, and so it says the improvement is 0.928, which is equal to the relative reduction in RSS. So before, when we had this the 5 data points, our RSS was 44, okay. When we made that split between I think at 3.5, okay, the resulting RSS was 3.1667, okay? So if you look at how much was reduced, okay, 44 minus 3.1667 is basically a reduction of 40.833, okay? And so if you do 40.833 divided by 44, you get that number 0.928, okay? So that's where this improvement number or this complexity parameter is coming from. It's saying this is how much it's improving. All right, so we get this. So the RSS is reduced by 92.8%, and so that's where it gets this complexity parameter. This will come in later when we talk about like pruning the tree, which I think is actually the next page here. All right, but is that okay? Where this complexity parameter comes from? It's saying after you include this node, the resulting RSS is, a smaller number, and how much did it get reduced? It was reduced by 93%, okay, which is a lot. That's a lot, right? So we've explained, 93% of the variation there, okay? You can graph these trees. If you say plot tree, it draws this, okay? This is like the most boring tree, okay? But basically it shows the relevance parts, right? x is less than 3.5 is, and if it's a yes, you go down to the left, and if it's a no, you go to the right. Okay? And then it shows you the value you predict. If it's less than 3.5, we're going to predict 1.667. And if it's greater than 3.5, we're going to predict 7.5. Okay? You actually have to call two commands, the plot and then add the text, and you get this. There are other packages. One is called Party Kit, okay? R Party Kit. Package Party Kit. And it makes like prettier trees, okay? Like the trees that result, get these nice little circles and stuff, and then it's like, ooh, that's pretty. But I mean, it's effectively gonna have the same information here, okay? And you can look up package Party Kit. I guess it's a play on kind of the recursive partitioning. I don't know. Okay. Something there, okay? Is that all right? Okay, I think we kind of talked about this already, the regression trees for larger data sets. So in our toy example, we only had one variable with 5 values. So we had 4 possible things, okay? If our thing had a second predictor variable with 5 values, we would also consider all possible splits using the second variable, another 4 options. And of all 8 possible splits, we would just choose the one that has the greatest reduction in RSS, right? And it just keeps going. So if we had 5 variables and 100 observations, and assuming all of the variables are unique in each of the, or all of the values are unique, we would have a total of 5 times 99, or 495 partitions to consider, right? We would have 99 partitions on the first variable. If we've got 100 unique values on the second variable, 99 partitions there. And then so we would look, so we have the computer compute the resulting RSS for all 495 possible splits. And then we say the best of these 495 is the one we pick, okay? And then so now you split the data into 2 groups, and then and you do this recursively. So probably on the first one, you're going to consider, like, I don't know, maybe it splits the data 70-30, okay? So now you have 5 variables, 70 observations. So you've got 5 times 69, I don't know what that is, 345, okay? And the computer will look at all 345 possible splits. It picks the best out of the 345, and maybe it splits it into 20 and 50, okay? And then again, it just keeps going down until it reaches some stopping criterion, okay? And so the stopping criterion might be keep going until the terminal node has 10 observations, okay? If it has 10 observations, stop. Don't even try considering splitting it. I think the default is like 20 observations. These are just arbitrary stopping criterion, okay? There's no rule that says 20 is best or 10 is best or 5 is best, okay? You just say keep splitting, and if you're getting better RSS, consider the split until you reach some kind of rule. And maybe the rule is if the RSS doesn't improve by this much, don't consider it, okay? Or the rule is, go up to like 4 levels deep, okay? Or the rule is the minimum number of values in your thing has to be 20 or something like that, okay? So you just keep doing this, okay? Is that right? So that's kind of where the recursive part of the recursive partitioning comes in, but it's just this idea of continuing to make these splits on all of these things, all right? So after the splitting, we repeat the process on the resulting 2 nodes. We consider all possible partitions across all possible predictors. Choose the partition that results in the greatest reduction in RSS, okay? And again, it's a greedy thing, so we just look at all of these and we say this one's the best, so we're going to do with that. Now, that might not result in the, quote, most optimal tree, okay? Because the most optimal tree ever might have to require us to kind of look ahead and say, like, you know, maybe we make a suboptimal choice so that we get an even better choice later down the road. I don't know, you know. You know, we don't have that right now, okay? All right, and so we do that till reach some stopping criterion, such as a minimum number of observations in each resulting bucket or partition, or a maximum tree depth. And then it's going to assign a single prediction value, y hat, to each bucket or terminal node. And for regression trees, we just use the mean of the observations in that bucket or terminal node. Okay. And so if you end up with 10 terminal nodes, your regression tree is only able to make 10 unique prediction values, okay? Which may or may not be a lot, considering what you're talking about, right? So you know, in regression, generally your regression model can predict an infinite number of values, right? It's some kind of, you know, you're adding this and this and this, and some you're scaling them, and so you've got a infinite number of values your regression model can predict. With a tree, you're only going to predict a discrete number of different values, and it's all based on how many terminal nodes you have. Okay.
Question. Yes.
What is so greedy about this? What do you mean by
The greedy is, right, so here we have 8 possible partitions, and how do we choose which partition we want? We just choose the one that is best in this immediate decision. Okay, so before the partition, our RSS is 44, okay? And we can say, all right, let's consider all of these splits, and looking at, like, the x1 variable, the split was at 3.1667, but, you know, we could have a fictional second variable, and maybe the resulting RSS for this potential split is 2.1. Okay, and so in this case, we're going to pick this split at 2.1, and we just go with, because it gives us the best improvement at this point in time. Okay, there's other algorithms that are, like, much more computationally expensive. Okay, and so it looks at all possible splits, like maybe two moves in a row. Okay, so it's going to say, okay, I can consider splitting it at 1.5 now, and then at this other spot in the next step, or you know, at this point now, and then, and it could turn out that that this split may not be like the best possible split now. Okay, I'm trying to think of a relatable example. Oh, okay. All right, your decision to come to graduate school, right? Okay, so let's say your optimization algorithm is, I don't know, like the decision-making criteria is what will maximize my income or something, right? Okay, so a greedy algorithm in this thing is going to say, okay, this immediate decision, is it going to increase my income or not, right? And I've got possible choices, and I'm going to choose the one that's going to increase my income at this very moment, right? And so if you did that, it might be like, after you graduate high school, we're going to assume you finish high school, the next thing that's going to maximize your income in that moment is going to be to get a job immediately, right? Because that's going to increase your income. But as you know, all of you went to college, right? Probably, you know, I don't know, different things, right? People in your life counseled you and said you should go to college or whatever. And that was because you said, well, if I become a student, that will not maximize my income in that moment, but the idea is that afterwards I can maximize income later on, right? And so the greedy algorithm says what is best right now, right? And so it's going to do a split right here because it gives an improvement, an immediate improvement right now. Whereas there's other algorithms that, have to think about the future, or like think about like other possible splits that it could make in the future, that says like, okay, first we got to make this split that gives us very little improvement, but by making this split here, I can get a lot of improvement later down the road. Okay, so kind of like, going to school is very costly. Okay, and if you're looking only at immediate benefit, okay, going to school is not a beneficial thing, right? And so a greedy algorithm is looking only at this next immediate step, and it does that. So not necessarily going to give the best result if you look at all possible splits on everything everywhere. Okay, it's just looking for this one split. What's going to give me the best for one immediate split right now? Does that kind of?
Immediate gratification.
Yes.
It's
So
not greedy in terms of computing power that it needs or anything.
yeah, no, this is greedy in that it's immediate gratification. Yeah, exactly. I guess that's a better non-delayed gratification algorithm, but we just call it the greedy algorithm, right? So that's what it is. It turns out delayed gratification is a huge predictor of childhood success. I don't know, all these cognitives. I don't know how well these things are, right? But they did we looked at these 5-year-olds and can they resist eating the M&M if you promise them more M&Ms? And then they looked at who graduated high school, and then they're like, oh, the 5-year-olds that didn't eat the M&M, so they could wait for the bonus M&M, more of them graduated high school or something.
Test your kids?
I did not. I got two.
Pass that window?
I have 2 kids, huh?
Are they past that window?
Well, one's gonna turn 6 next month, and then the other one's 2, and they have different personalities. Yeah. I don't know. All right. I should not say anything that's gonna embarrass my kids in class. All right. Okay. So anyway, now that we call them trees, then we decided to stick with all of these tree analogies and gardening things, okay? And so now we talk about pruning a tree, all right? And so if you got a big data set, this is often an issue, is that you follow the above thing where you consider all these splits and you keep going until you reach some kind of stopping criterion, okay? And so you might end up with a tree with 6 levels deep, and each node has 10 observations in them, okay? And you if you got 1,000 observations in your original data set, you might end up with 70 different terminal nodes, okay? And maybe that's a good tree, or maybe that's a tree that has overfit the data, okay? Maybe you have decided that back here for this thing, they could have gotten better performance, right? So here this is one terminal node for Obama wins these counties 383 to 70, but they might have gotten marginally better performance if they said does the county I don't know. Does the county start with the letters A, D, or K? And if the county starts with the letters A, D, or K, maybe just coincidentally in the data, the counties that started with A, D, and K, voted for Clinton or something. And so we're going to say okay, let's split the data so that if the county starts with A, D, or K, we're going to say it votes for Clinton and it doesn't, right? And we could coincidentally from the data, that might give an improvement in RSS, okay? But the question is like, is that really like something that's going to help us predict what's going to happen in the future? Like if I follow this tree and I go, oh, the county started with the letter D, therefore, we're going to now predict Clinton or something. Like that doesn't make sense, right? Logically, that doesn't make sense. But something like that could appear in the data, right? There could be just coincidental things in the data where, it looks like there's some kind of relationship, right? And so if your thing is just like keep going until you get some improvements, until you have like a minimum number of observations, you can end up with these, suboptimal splits. Okay, so what we might want to do is we will want to consider pruning the tree. And so pruning the tree says, okay, we've split the data, and then we are going to get rid of the splits that did not improve our RSS by very much. Okay. And so here I have R, create a tree, okay? And this is like, don't use these control because this is going to give you a terrible tree, okay? But anyway, I purposely told R part, I gave it these conditions, and these are conditions to make a terrible tree that's going to keep splitting until each node has basically one observation in them, okay? And so here I'm just doing it to my toy data set with 5 things, and I say, still consider a split even though you only have 2 observations there. And so basically, I end up getting 4 terminal nodes, okay? Because I have 4 different observations of values of y, and so I got one node that puts these 2 together, one node that puts this observation there, one node that puts that observation there, and one node that puts that observation there, all right? And so, is this a good tree? Probably not, right? This is not going to be a good tree. And so, what we're going to do is we're going to tell R to get rid of the kind of the worst split, the worst split here, okay? And so when we look at this, okay, if we look at kind of the node of the tree here, we can see that at the top level we started off with an RSS of 44, and then when we split it we end up getting this node has a deviation of 2.6 and this node has a deviation of 0.5, so the total deviation is 3.167, okay? And then afterwards, if we split, so the first one splits basically between 3 and 4, so it puts these 3 together and it puts these 2 together, okay? If I split these 3 observations into 2 nodes, we can predict these 2 values perfectly and this value perfectly, and we're going to get 0 deviation. And that's what we have here, okay? Values less than 2.5, there's 2 observations there and there's no deviation. And then values greater than 2.5, there's 1 observation there and there's no deviation, okay? Similarly, the other one's a value less than, so greater than 3.5 but less than 4.5, there's 1 observation. Greater than 3.5 and greater than 4.5, there's 1 observation, and there's no deviation there, okay? So if we look at this, right, how much improvement did we get, okay? By including this split, the RSS went from 2.66 down to, I add these 2 together, down to 0, okay? So how much improvement is that? That's a reduction of 2.66 or 2.667, okay? And as a fraction of the total RSS, if I do 2.667 divided by 44, that's about a reduction of around 6%. Okay, so by including this additional split at 2.5, I went from a deviation, total RSS, residual sum of squares of 2.66 down to, I add these 2 together and I get down to 0. Okay. Over here, if I include the split at 4.5, okay? So before that, I didn't have a split and we had two observations that were greater than 3.5, and my RSS there was 0.5. By including this additional split at 4.5, okay, my RSS went from 0.5 down to 0. I had 0 plus 0, and so it went from 0.5 to 0. So that's an improvement of 0.5. So if I do 0.5 divided by 44, so the total RSS in the beginning was 44. If I do 0.5 divided by 44, I get 0.0114, okay, around 1%. Right. Is that okay where these two numbers are coming from? The 6% and the 1%? Okay? All right, and so these will show up as the complexity parameter of including this split here, okay? And so between these two, okay, this has a complexity parameter of 6%, this one has a complexity parameter of 1%, and I didn't write it here, but the first one went from 44 down to 3.16, which was 2.6 plus 0.5. That was like a reduction of like 92%, right? 93%. And so those numbers show up here if you ask for the summary on this, this tree, okay? And so we have the different possible nodes, okay? The node at here, which was the first split has a reduction of around 93%. The next one has a reduction of 6%. The next one has a reduction of 1.1%, okay? And this 0.01 is basically my stopping criterion, okay? And so we can see the first one, splitting for 3.5 to the left and not has a complexity improvement of 92.8% or improvement of that, okay? And over here, okay, our complexity parameter is 0.0606, okay, which we showed how we arrived at that, okay? By including this, we have improved it, improved the thing by 1.667, okay? The improvement here is 1 because we reduced it from 1.667 down to 1, which as a proportion of this data is 100% of the error in this, of the RSS in this node, okay? But compared to the original data of 44, it's only around 6%, okay? Over here, we went from an RSS, I'm sorry, not RSS of 1.66, an RSS of 0.5, okay, down to 0, okay, and that's a complexity parameter of 0.01, okay. Because it went down to 0, it's technically 100% of the reduction there, okay. And so anyway, this basically says this is the weakest link, so if we're going to prune it, we should remove that one, okay? And so the command there is you start off with your original tree, okay? So here's TR1, the one that has 4 terminal nodes. You throw that command into the function prune. So we say prune tree1, okay? And use the resulting splits have to have at least a complexity parameter of 2%, okay? Which is above that 1% threshold. And so you can see that it got rid of, or it got rid of the last split there, okay? That weak split where the complexity parameter is only 0.011, okay? All right, and here if I say the complexity parameter needs to be at least 0.1, okay? So if I prune, the first tree and I say complexity parameter must be 0.1, then we get back, sorry that it got split on 2 pages, basically the tree that we had in the beginning, right? It doesn't include making the split at 2.5. Is that okay? How the tree pruning works? All right. So there's a question, how do we choose a complexity parameter? This is not an easy question to answer, okay? There is a nice little function in our part that kind of gives us a nice picture that makes it so we don't have to do as much thinking, okay? Now, whether that's a good thing or bad thing, I don't know, okay? Right? Anytime you have an automated system where you don't have to do any thinking, it's nice, but maybe you become overly dependent on it and maybe you don't make the best decisions very easy. Very well, okay? But anyway, what this does is there's a function called plot CP for plot the complexity parameter, and it does cross-validation, okay? And it's going to do 10-fold cross-validation, I think, by default. And it kind of fits a whole bunch of different subtrees to kind of figure out what's the best complexity parameter. Now, so last week you guys did cross-validation, right, in your homework, and there is a, was it on your homework? Not your homework. Okay, not your homework. Okay, it's going to be in your homework
Here,
next week.
yeah.
Next homework. Sorry.
We did here.
We did it here. Okay. Yes. Next homework I'm assigning, there will be cross-validation. Yeah. Okay. There's a random element to it. Okay. So 10-fold cross-validation splits it into 10 random partitions. Okay. But if I did 10-fold cross-validation and you did 10-fold cross-validation, my 10 random folds will look different from your 10 random folds. So you can do this and you might get slightly different results when you do it. Now, how much of a difference does it make? It could make a little difference, okay? The documentation that comes with plot CP is, it says a good choice for a complexity parameter for pruning is often the leftmost value for which the mean lies below the horizontal line. The horizontal line is one standard error above the minimum value. So here, let me just show you this picture here, okay? So here I think we are looking at some data set about cars, okay? We're looking at, I guess, consumer reports data on vehicles, and we're trying to predict the cost of the car, I don't know, based on stuff like fuel economy, whether it's a compact, large, or medium car, and then the country that it was manufactured in, okay? This is like old data, right? So I don't know how good of a model you have. And so anyway, so here we just say, go ahead and make, I just use the default settings, and it made 7 terminal nodes, okay? And so first it's split between compact, small, sporty, and vans in one category, and then the other it puts large and medium, okay? So this is kind of the first level split, okay? And then it further split the compact, small, and sporty, and van cars into cars that came from Brazil, France, Japan, USA, Korea, Mexico, and USA. I cannot name a single Brazilian car. I don't know. I'm sure they manufacture, there's Brazilian car manufacturers, but I don't think we have them in the US. Okay, anyway, so we have that, and then, they further split it into this and this, and these are kind of the terminal nodes that we get. Okay, and all right, so this is what we have, and here it says, here's the size of the tree. You can have 7 terminal nodes, 6 terminal nodes, 5, 4, 3, 2, or 1, okay? So one terminal node is basically everything in one group. There's no reduction in it, right? So here's basically with one split, and if you do another split, and here's another split, okay? So here, when we did cross-validation, that's what this xval is, okay? When we did cross-validation, it turns out that we got the lowest cross-validation error when we had 5 terminal nodes. Okay, when we had 5 terminal nodes, that was the best performance that we got. Okay, we didn't when we had 6 or 7 terminal nodes, it actually went up a tiny bit. It's hard to see, but it went up a tiny bit, right? So and that could happen, right? Because when you do cross-validation in your training set, maybe you decided to split on counties with A, B, and C versus counties that didn't have that letter. And that turned out not to be a good predictor, so that when you did the cross-validation, you find out, oh, this was not good for predicting, right? Okay, so this was the lowest cross-validation error we have. And there it gives it also an estimate of the standard error of this number, right? So here it just says, so the idea here is with tenfold cross-validation, you're trying to predict the amount of error. So you have 10 folds. Here, let me just kind of draw a picture here. Okay, so if we have 10-fold cross-validation, okay? So here is, so we've got, so we train on this, and then we validate on this chunk, okay? And so basically, this produces, from the training data, we get this kind of tree, right? And then we plug in the validation data, right? And this says, you know, we're going to predict 0.5 and 1.2 and 3.1 and 4 and 2.6 or something, right? Okay, and then so you plug this in, and when you plug it in, you get a y hat. It's going to predict one of these values, maybe 0.5, and then the actual y was maybe 0.9, right? And then over here, maybe it predicted 1.2, and the actual value was 1.2. And maybe over here, you plug in something, and you go down these 2 branches, and you end up at 2.6, and the actual value was 0.2 or something, okay? And so the error is going to be 0.5 minus 0.9 squared plus 1.2 minus 1.2 squared plus 2.6 minus 0.2 squared, okay? And then so here you get some RSS, okay? And then we do this again with a different, so this was fold 1, and now we do it again with fold 2, okay? With fold 2, maybe our tree looks different, okay? Maybe it looks like this, and we predict 0.6 and 3.1 and 2.8 and 1.7 and 1.6. I don't know, okay? We get a different looking tree is the point, because you had different, because your training data is different here than it is here, because it's a different random fold, your tree ends up looking different, okay? And so anyway, you still want to figure out what this is, and you get your y hats, and then you have your actual y, and then you get your error, and you're going to get some, you know, another RSS value. So this, you know, let's say this ends up being, I don't know, 0.4 squared plus 2.4 squared. I don't know, 6.5, okay? So I'm just making that up, okay. And then, you know, you plug in these values, you plug in these values, and maybe you get 7.2 or something, okay? And you're gonna get 10 of these different things, right? And so your prediction for this RSS, okay, and technically we do the mean squared error, okay, is gonna be different, and it's gonna have a standard deviation associated with it, right? So we're gonna get different, we have, we end up with, so we get RSS, and then we calculate the mean squared error. For this, we do 6.5 divided by the number of observations, okay? And so we're going to get, we get basically 10 different MSE values, okay? One for each fold. And so anytime you have 10 different values, you have a standard error as well, or a standard deviation as well, okay? So there's a standard deviation of the MSE values, okay? And so that's where that's what this, where is my picture? That's what this vertical bar is, okay? So here, you know, we're saying when you had the 5 trees, I'm sorry, a tree where you ended up with 5 terminal nodes, that gave you the best cross-validation performance, okay? But you still have different amounts of error for each of those folds, and so there's a standard error there. Is that okay? And so we say, you know, even though this is the minimum, technically, at least statistically speaking, this value is not statistically or significantly different from this value, okay? Because it's still within like one standard error here. Okay, so we're going to say like this value is not significantly different, this value is not significantly different, even though it's a little bit higher. All right, and so the rule of thumb is you say, well, generally you should pick the tree of least complexity where you're still getting performance that's like comparable between the two. Okay, so and according to this picture, this value is not statistically different from this value, and so therefore we should pick the tree that is least complex, okay, kind of like an Occam's razor thing. Pick the least complicated model that you can that still gives you performance that is good. So in this case, we say, let's pick a tree with 4 terminal nodes. Even though we got better performance with 5 terminal nodes, the performance of the 5 terminal nodes was not that much better than having only 4 terminal nodes. Is that okay?
So we're choosing it because it's less, right?
We're choosing it because it's less complicated. And we're saying, even though it's less complicated and doesn't perform as well, the performance decrease is not significant enough for me to worry about. Okay, good. You know, it's all a guess, right? It's all an estimate. Okay, I mean, we don't like to hear that, but it's just we plugged it into cross-validation. We got this number. We plugged it into cross-validation. We got this number. Okay, and we said, okay, well, 6.5 and 7.2. And we get a bunch of different numbers, and we say, what's the standard deviation of these things, right? If we plugged it into cross-validation and our RSS was like exactly the same every single time, then we're like very confident on what the RSS should be, okay? But because it's not going to be exactly the same every time, we have a standard deviation associated with it, right? So, you know, in all of statistics, we're trying to distinguish between, you know, we got 2 things that have different means, and the question is, are those means significantly different, or are they just a little bit different on paper, but the difference isn't meaningful, right? I don't know, okay? It's all, we do the best we can. And again, and so to make matters even worse and more uncertain, okay, is that because cross-validation is subject to random error, or not random error, random sampling, someone else could ask R to make this exact same picture using the same command, but they get a different thing, right? So I did that, okay? So I said, all right, we do the same thing. Okay, so anyway, I say, okay, sorry, before I'm jumping ahead of myself. So based on this picture, we say the complexity parameter I should use is 0.074. So I say, okay, prune the tree to using complexity parameter 0.74, and I get a tree with 4 random nodes, okay? All right, here I do the exact same command, but here I set a different random seed, okay? I said set seed 11 instead of whatever other number I did, okay? And so when I did this, the best performing tree had 5 terminal nodes, and 4 terminal nodes did not perform as well, but this time 4 terminal nodes, this mean is above this dotted line, okay? So according to this diagram, which was called using the exact same command that produced this diagram, okay? According to this diagram, it says I should use a complexity parameter of 0.026, okay? And this makes you uncomfortable, right? Because it says, well, how do I know if I'm doing it right, okay? Well, you don't, all right? That's all of statistics, okay? And I know we want to be able to just plug something in and just get and know like this is the right answer, okay? But we don't get that luxury. We don't get that. It's not like math where you follow like the laws of the universe that you've defined and you say this is going to lead to this natural conclusion and this is right as long as we're talking about Euclidean space or whatever, you know? We don't have that beauty. It's messy. It's data, right? You don't even know if the data that you have is like 100% accurate, right? So like we always have to keep that in mind too, right? That like how reliable is my data, right? If the data you've collected or somebody gave to you is junk, like it doesn't even matter what analysis you do. It like you're gonna get junk results, right? If the person conducting the survey didn't know how to ask the questions properly, like don't even bother wasting your time. I'm always this is a side tangent, but there will be people like on Facebook, it'll be like, please help me fill out this survey, right? I've created this Google Forms and I'm emailing it out and I'm like, and I always just want to say like, your survey is useless because it's not going to be representative of anything, right? Like who's going to respond to this survey? Like maybe your friends, which all think like you, like you're just going to get like, you're going to think, everybody thinks like you or something, right? Or maybe it ended up on some, message board where it's full of people who like to troll internet polls, and that you're gonna get something like Bodie McBoatface or something, So anyway, this is just, we're gonna assume we have good data, and even then, because of randomness, we get slightly different results. According to this, we should choose 5 terminal nodes instead of 4, okay? Now, the difference isn't super great. It's not a huge difference. Do we end up with 4 terminal nodes or 5 terminal nodes? Probably the implications of such is not life-altering as well, okay? And then so then you have to take your knowledge, your personal knowledge and personal experience to decide, does it make sense to make this split, right? If you know something about cars, you can say, well, does it make sense to say, I don't know, using this variable to predict price, is that going to improve or not? And that's something you have to do. So if you go for any kind of data science job, you should have knowledge of basic things in the data to begin with, right? I've had students go to like these data science type startups, and some of them I worry about because it's like a data science startup is just like, oh yeah, we'll take your data and we'll analyze it, but it's like, here's medical data, and not a single person in the startup is a doctor and has any interpretation. It's like, here we got some medical data on like kidney patients, right? And nobody knows what any of these numbers mean, all right? And they're just like, well, let's throw it into the computer and see what we can get, all right? You're gonna have a terrible, terrible model at the end of it, because you need somebody, like a kidney doctor, that can say like, oh, well, obviously, we should be looking at this variable, right? Or like this result doesn't make any sense, right? And if nobody has any kind of that domain-based knowledge, you're gonna get something that just doesn't work, right? So you need somebody, even if they don't know anything about computers, just like say like, oh, you're a kidney doctor, like, please help me, tell me if this even makes sense, right? So you need to have that. So I worry about some of these startups that just get in over their head and say like, oh, we'll do anybody's data. Somebody should be knowledgeable about something there. Okay, but anyway, at least both of the graphs agree that 6 or 7 nodes is not going to improve, and the question just comes down to, do I have 4 or 5 terminal nodes? This is not the consequences of, quote, making the wrong choice, and there's not really a wrong choice, okay, is okay. All right, why don't we pause here? We'll take a 10-minute break. We'll come back. We'll look at classification trees and all of these methods for improving tree performance.